Okay, now we're going to talk about rotation in 3 dimensions. So, two-dimensional rotation is actually a special case of three-dimensional rotation. We only deal with x direction and y direction, but instead of dealing with only x and y, we would need to consider the axis of x. So, if we project the xy plane, just like what you see in the plot over here, we are rotating from x naught y0 to x1 y1 with an angle theta over here. Now, if we are trying to find out the three-dimensional representation of this transformation, what are we going to do? Over here, it is clear that the theta is related to xy plane. So when we are dealing with the cosine and sine term, we actually do not need to worry about the direction along z, which means the projection along z direction is its unit vector, which is 1. So r z theta can be treated as this is cosine theta, sine theta, negative sine theta, cosine theta. So far, this is the same as what we deal with in the previous slide. That is only deal with two-dimensional coordinate. In z direction, since we're not doing any rotation, so the component projected along z direction is going to be 0. Same here. And along the z direction, it's going to be 1. So if we are rotating everything about z direction, this is the matrix that we need to take care. Now, how about if we are rotating things along xz and yz plane? What are we going to deal with? Before we talk about that, this is the conversion matrix that we're going to deal with. Just like what I said earlier, this is going to be the matrix that we need to convert from zero's coordinate to the first frame. So this is going to be something we need to do the calculation. If we are dealing with rotating about x-axis, what it's going to look like. Keep in mind when we are doing something like this, we need to rotate from x to y, y to z, z to x. So when we are drawing this thing over here, we are talking about the rotation in this direction with an angle theta. So when you look at this diagram over here, you are talking about theta over here. So the distance between z-axis and this point over here is going to be cosine theta over here. This is going to be our sine theta. In other words, if we try to deal with the transformation matrix Rx theta, we would need to do another matrix. When we do the matrix, keep in mind we are rotating about x-axis, which means it must be 1 along x-axis. And we need to fill out the 4 components over here. So let's start from y. Y is going to be in this direction. So we're going to have our cosine theta along y0 direction. Along z direction, it's going to be sine theta. And this one is not rotating about this point. So when we are dealing with that one, the x component along this column is going to be 0. For this one over here, we are talking about this point over here. So the distance between this point and z-axis is going to be sine theta, but keep in mind when we project this distance over here, it's going to be along the negative y naught direction. So we're going to have a negative sine theta over here. Along the z direction, it's going to be cosine theta. And again, we do not have any projection along x0 or x1 axis. So this one over here is going to be 0. Same for these two components. So this one over here is going to be the transformation matrix when we are rotating about x-axis. Now, let's talk about if we rotate about y-axis. Keep in mind we are dealing with x to y, y to z, z to x. So the rotating is going to be like this. And we're talking about theta over here. So ry theta is going to be something like this. And we are rotating about y-axis, which means we have a component 1 over here along y-axis. And the other parts over here, let's start from x direction. So we're going to project it over here. This is going to be cosine theta. This part over here is going to be sine theta. So let's put everything into this matrix. So we're going to have cosine theta in this component, and we do not have any projection along y-axis. So this component over here is 0. Along z component, we're going to have negative sine theta. For the second component, since we are rotating about here, it's going to be 0 and 0. For the z1 axis, we do the same projection, which means theta is going to be over here. So along x direction, we're going to have sine theta. We do not have any projection along y-axis. For the z-axis, is going to be cosine theta. So if you have rotation about x-axis, y-axis, and z-axis, these three transformation metrics are something we need to deal with. I would suggest you keep those kind of things handy with you. So every time if you need to refer to the metrics, those three matrices are always somewhere you can look up. You can keep this set of PowerPoint slide with you, so you have better idea what's going on when you are doing your test or your homework. Let's deal with one of the example. Okay. So let's say we have a vector that I want to describe in zeros uh, called frame, and the xy components are 0, 0, and 1 separately. And this is going to be rotated about y0 or y0 axis by pi over 2. So we can do our y theta that use this metric, this formula. So the matrix is going to be cosine pi over 2 is going to be 0. Sine 90 degree is going to be 1. So this is going to be -1. Second column, nothing fancy, just copy this column over here. For the third column, again, sine 90 degree is going to be 1, 0, and 0. So the transformation matrix is going to look like this. Now, we try to find out this one, describe it by ry pi over 2. Then we are using the transformation. Then you're going to get your answer equals to 1, 1, 0. So this is how we deal with the transformation using the when we are dealing with rotating along a specific axis. This is something we're going to deal with. Now we're going to talk about similarity transformation. So each transformation matrix can be viewed as a transformation. When we are dealing with the rotation, we are trying to convert from one specific orientation to the other one. So when we are describe the position of a specific point using an after a rotation, we will need to do a transformation, and we can use the matrix we developed earlier. So this is something you might need to take a look of the textbook and go through the examples we have in the textbook. There is one other thing that I would like to get your attention. Suppose we have A is a transformation described in reference frame 0, and B is the same transformation but described in frame 1. And R10 is a coordinate transformation from frame 0 to 1. So if you have an A that is maybe rotated about x-axis or y-axis, or it's actually a combination of two. So you got frame 0, you got O1 over here. So when you are dealing with a rotation, three-dimensional rotation over here, so you might rotate it about here, and after a while, you try to convert from, you know how to convert or transform using this coordinate, but in this coordinate, we must have something corresponding to the transformation, because this one rotating over here is in space. It might fix to the joint over here. So when you view from frame 0, it is going to be different from you view from frame 1. So we need to find out the transformation based on different frames. So when we are dealing with that, the one we're going to deal with is, okay, so if we know it's going to be rotated about x-axis, then about y-axis. In that case, we got the transformation matrix A, but that is based on frame 0. Now, if I want to do the same calculation based on frame 1, then since we know how to convert from frame 0 to frame 1, which is something we have one example earlier. So if we know how to deal with that, then the transformation, the same transformation viewed from the first frame is going to be obtained by using this formula. B equals to the inverse of the transformation multiplied by A multiplied by the original transformation. Then we can find out the transformation matrix. Again, you do not need to deal with everything from scratch. As long as you know individual transformations, then you should be able to come up with a similarity transformation matrix based on what we have already. So this one over here is an example. So let's say, okay, I got the rotation about y naught axis, which is from the first frame. This is from the view of frame 0. Okay. Now, if we do know that from A to B, from frame 0 to frame 1, we do need to have a transformation matrix using this one. Then, if we know this object, let's say frame 0, frame 1, and we are describing P that is going to be rotated about something like this one is y naught axis. So we want to find out the coordinate based on this frame. So what we need to do is to find out the transformation matrix from here to here and take the inverse, multiply by the transformation matrix, which is this one. Then we take the transformation matrix from 0 to first frame. Then we got, if you try to find out the coordinate after rotation viewed from frame 1, that is how we're going to obtain our transformation matrix. So composition rotations. However, when we are dealing with many rotations, you might think, okay, so you might say that I want to do something like x naught, y naught, and z naught. Step 1, rotate the bell x naught for pi over 6. Step 2, rotate the bell y for pi over 3. Step 3, rotate about z for negative pi over 10, so far and so on. Okay, so you got a sequence. Can we say that, okay, since I know all the sequence, I know it's going to be x, y, or z with a specific angle. Can I rotate step 3 first? Then we rotate step 2. Then we do step 1. Can we do that? The question is, step 1 to step 2 to step 3. Is that going to be step 3, step 1, step 2? The answer is no. It's not going to be the same. So when you are dealing with those kind of transformation in a sequence, you need to be careful. You cannot switch the sequence of individual movement or rotation. The result is not going to be the same. In other words, the sequence must be in a specific sequence. Interchange the sequence. Well, oops. Well, yield wrong orientation. So this must be remembered. You cannot just interchange the sequence based on what you want. The sequence must be specific if you want to have a specific rotation or orientation of the object. That is going to be important.